All right, in the last video, we looked at the basics of 2D projectile motion and how we extended 1D motion into 2 dimensions with our kinematic equations. And we looked at a simple example. So now we're going to look at some more examples of projectile motion. Here's another example. A dart is thrown horizontally at 10 meters per second toward a bullseye on a board. It hits at point Q below the bullseye 0.19 seconds later. So part A, what is the distance from the bullseye to point Q where it hits? And B, how far away from the dartboard was it released? Okay, so how are we going to do this one? Well, we know how long it takes to get to the wall. And we know its initial velocity, and the initial velocity is all horizontal. All right, since the initial velocity was all horizontal, the vertical motion is the same as if we just simply dropped it. So the distance below the bullseye where it hits is just the distance that it falls in the time it's in the air. And the time it's in the air was given as 0.19 seconds. So we get delta y equals 1/2 gt squared. And plug the numbers in. We get 0.5 for the 1/2, 9.8 meters per second squared for g, and the time 0.19 seconds, and then we square that, and we get 0.18 meters. So 18 centimeters is how far below the bullseye it hits. All right, so how far away was it? Well, we know the velocity is 10 meters per second, and we know it takes 0.19 seconds, so we just take velocity times time to get the horizontal distance. The horizontal distance is just velocity times time, so 10 meters per second times the 0.19 seconds, 1.9 meters. Okay. All right, here's another example. You throw a ball toward a wall at a speed of 25 meters per second and an angle of 40 degrees above the horizontal. The wall is 22 meters from the release point. How far above the release point does the ball hit the wall? What are the horizontal and vertical components of the velocity when it hits the wall? And part C, has the ball passed its highest point in its trajectory when it does hit the wall? All right, so I've drawn a diagram here, and we're given the initial velocity in both magnitude and angle, and we know how far away from the wall it is. All right, so if we want to get part A, how far above the release point, that would be the y position, we would need to know the time it takes to get to the wall. Well, we know how far it is, and we know the horizontal component of the velocity, so from that we can get the time. The time would just be the distance divided by the horizontal velocity. All right, so first let's find both the horizontal and vertical components of the velocity. So we're given the angle is 40 degrees above the horizontal. So in the x direction we have v naught cosine theta, and in the y direction we have v naught sine theta. And then we also know that the distance delta x is v naught xt. So t then is going to be delta x over v naught cosine theta, where delta x was given 22 meters, the v naught was 25 meters per second, and then cosine of 40 in the denominator. So we crunch those numbers, we get 1.15 seconds. So that's how long it takes to hit the wall. Now we know how long it takes to get to the wall. We can write our position as a function of time in the vertical direction and get how far it is in the vertical direction, or how high above the release point. All right, so we have delta y, how far it goes in the y direction, equals v naught yt minus 1/2 gt squared. And so we plug in for v naught y is v naught sine theta times t minus 1/2 gt squared. The v naught is 25 meters per second. And then we have sine of 40. We have the time we found in the previous step, 1.15 seconds. And then the minus 0.5 for the 1/2 9.8 meters per second squared for the g, and 1.15 seconds squared for the time. I crunch those numbers, we get 12 meters. So notice the displacement is positive, so it's 12 meters above the release point. So we've got the answer to part A. How far above the release point does the ball hit the wall? Well, it's 12 meters up. Now part B. What are the horizontal and vertical components of the velocity when it hits the wall? Well, since we only have acceleration in the vertical direction, the horizontal velocity is the same as the initial horizontal velocity. So that's just v naught cosine theta. So 25 meters per second times cosine 40 is 19 meters per second. That one does not change. For the vertical component of velocity, we got v0y minus gt. So I've got 25 meters per second times sine of 40 minus the g and the time at 1.15 seconds, and we get plus 4.8 meters per second. So we've got the horizontal and vertical components of the velocity. Notice that they are both positive. So since the vertical velocity is positive, that means the ball is still moving up when it hit the wall. So now it's easy to answer part C. Has the ball passed its highest point in the trajectory when it hits the wall? Well, since our vertical component of the velocity was positive, the ball was still moving in the upward direction when it hit the wall. So no, it has not passed its highest point. So again, we see that the final velocity components are both positive. So the y component of the velocity is positive, meaning it's still moving upward. If you throw a ball at an angle, it will follow a parabolic path. All right? So since the vertical component of the velocity is still positive, still moving upward, we have not reached the highest point in the path. So we have not passed the highest point in the trajectory when it hit the wall. So if our velocity had come out negative, that meant that it already reached the highest point and was starting to come back down when it hit the wall. But it didn't do that. The velocity was still positive, so it was still moving upward. All right, here's another example. This is we're playing volleyball. So we have a volleyball net is set at 2.24 meters above the floor, and the court is 9 meters by 9 meters on each side of the net. Using a jump serve, a player strikes the ball 3 meters above the floor at a horizontal distance of 8 meters from the net. If the initial velocity is horizontal, part A, what minimum speed must the ball have to clear the net? And then part B, what is the maximum speed of the ball so that it will land in bounds on the other side? All right, so for part A, we want to make sure we give the ball an initial velocity that's large enough so that it will clear the net before it falls too far. If it's too slow, it will fall below the top of the net before it gets to the net. So for part B, we want to make sure we don't have it go too fast that it goes beyond the boundary on the other side and goes out of bounds. All right, so let's look at part A first. The player strikes the ball 8 meters from the net. So that means it's going to travel 8 meters horizontally, and we want to make sure it does not fall to the top of the net before it travels horizontally that net 8 meters. So how far is the top of the net? Well, she's launching it 3 meters above the floor, and the top of the net is 2.24 meters. So that means we want to make sure it's going fast enough that it can travel 8 meters before it falls 0.76 meters. So we find the time it takes to fall 0.76 meters. And so we have delta y is 1/2 gt squared. So multiply by 2, divide by g, take the square root. So we get t equals the square root of 2 delta y over g. So we have the square root of 2 times the distance it falls, 0.76 meters, divided by g. And the time then is 0.394 seconds. So it has to get to the net in 0.394 seconds or less in order to clear the net. So what speed? Well, we know it's going to go 8 meters, and it has to travel the 8 meters in this time. So we just use distance equals velocity times time, and velocity equals distance over time. So we have x equals v naught t. So v naught is delta x over t. So 8 meters divided by 0.394 seconds. So it has to be going at least 20.3 meters per second, or a little over 20 meters per second, rounded to 2 significant digits. All right, so we saw that it had to be going at least 20.3 meters per second to clear the top of the net. Now, if it goes faster than that, it will clear the top of the net. But if we go too fast, it will go beyond the boundary on the opposite court before it falls to the ground, and so it'll be out of bounds. So we want to make sure what's the maximum speed it can have so that it doesn't land out of bounds. So we do the same thing. We find the time it takes to fall all the way to the ground, and then find the velocity from distance over time, making sure that the distance is not beyond the boundary. So from the net to the out of bounds marker is 9 meters, and she launched it 8 meters from the net on the other side. So we take the 8 meters plus the 9 meters. So the total distance the ball will travel is 17 meters. We don't want it to go more than 17 meters. So the time, of course, we just get 2 delta y over g and the square root, with the delta y is the total 3 meters to the floor. So that means 0.782 seconds. So it has to fall in that time before it goes farther than 17 meters. So the maximum velocity then is the 17 meters divided by the 0.782 seconds, or 21.7 meters per second. So if we give it an initial velocity of greater than 21.7 meters per second, it will go out of bounds. And if it's less than 20.3 meters per second, it will hit the top of the net and not clear the net. All right, let's look at some conceptual questions here to see if you're understanding the 2D projectile motion. A golfer drives a golf ball from the tee, sending it down the fairway. So ignoring air resistance, what happens to the horizontal and B, the vertical components of the velocity of the ball? What are the horizontal and vertical components of its acceleration during ascent, during descent, and at the topmost point of its flight? So part A, the horizontal component of the velocity remains constant. Since the acceleration is only in the vertical direction, it cannot affect the horizontal velocity, so the horizontal velocity remains constant. So what about the vertical component of the velocity? Well, that's exactly the same as if we threw the ball straight up. So on the ascent, it's going to slow down, eventually run out of velocity and run out of speed and become 0 at the maximum height, and then the velocity increases on the way down. All right, so in the diagram here, we see the motion in the horizontal and vertical directions. The velocity vector is shown. So we see it follows a parabolic path. So our initial velocity vector is shown there, and we break it into vertical and horizontal components. The horizontal component of the velocity vector stays constant. It's always the same length. However, the vertical component of the velocity gets smaller on the way up. When we reach the highest point, the vertical component of the velocity is 0, but we still have the horizontal component. And then on the way back down, the vertical component of the velocity now points downward and increases in length as it gets closer to the ground. But the horizontal component of the velocity vector stays constant all the way through the path. Okay, now part C. What is the horizontal component of the acceleration? Well, we only have acceleration in y, so the horizontal component of the acceleration remains 0. And then finally, the last one, what about the vertical component of the acceleration? Well, that remains a constant 9.8 meters per second squared down, pointing down. So that stays constant down. All right, so that's all the parts to this one. All right, so that brings us to the end of the discussion on motion in 2 and 3 dimensions. We've looked at a number of examples, so you should have a better understanding of how to approach these problems. So next up in another video, we'll look at relative motion. So we'll look at motion of two objects and how the motion of one object appears to the motion of the other one. And we'll especially look at something that's in a moving reference frame.